Hello folks, and welcome back to another lesson here. Today's a big day. We're already moving on to chapter 3. And we're starting out chapter 3 by looking at solving systems of equations graphically. We'll talk about what systems of equations are in just a little bit. But before that, we need some foundational knowledge, which is, what does it mean for an ordered pair to be a solution for an equation? What does it mean is true for a point that is located on the line of a linear equation? Or in other words, which one of these is going to be our solution for this line over here? Is A right here going to be a solution? Is B right here going to be a solution? Or is C all the way out here going to be a solution? If you chose the answer B, you are correct. The key concept that we need to know going into this lesson is if a point is located on the line, on the graph of a line, then it's a solution. So if a point is on the line, that makes it a solution. Now, we're going to get into a system of linear equations. All a system of linear equations is two or more linear equations. So it means we're just looking at two, possibly three or four equations at the same time. What's the solution going to be? It's going to be what makes all equations true. And if we're looking at this visually, what makes all equations true? If we're looking at this graph down here, we know that for L1, what makes it true, what are the solutions, are all the points on this line. What makes L2 true, what are its solutions, are all the points on this line. So if we're looking for something that makes both equations true, we want it to be a point that's on this line and on the other line, meaning that visually, finding the solution is finding the intersection. It's the same thing when we're looking at graphs. Let's run through an example, and let's walk through the steps at the same time. Solving a system of equations by graphing. Step 1 is going to be graph the lines. Very surprising there, I know. Graph the lines. So let's graph these. We start at, for this first one, 6, and we go down 3 over 1, down 3 over 1, down 3 over 1. Now for these, it's very important that we're doing them with a straight edge, because we need these lines to intersect as accurately as possible. Fortunately, such a thing as a straight edge for a computer doesn't really exist, so I'm going to do my best to make this work here. There we have our line. Now we're going to graph the other one, 2x minus 4. So we're going to go down to minus 4. Then we're going to go up 2 over 1, up 2 over 1, up 2 over 1. Get as many of these as possible to make our straight edge or our straight line as straight as possible. From here, what do? We graph this line. Let's do another point down here. And we've done step 1. Step 2 is going to be find the intersection. To find the intersections, all we have to do is look for the place where these two lines intersect. we have our intersection right here at the point 2, 0. So that should theoretically be our solution. Our solution should be x is equal to 2 and y is equal to 0. Or we can write that as an ordered pair, 2, 0. Step 3 is going to be check your answer. How do we check? Well, we substitute both points in for both equations. So we're going to start off with this first equation by substituting in 2 in for x and 0 in for y. 0 will be equal to negative 3 times 2 plus 6. Or 0 is equal to minus 6 plus 6. These two sides are true, meaning that this is a solution for the first equation. Let's check with the other one. For the other one, we have 0 is equal to 2 times 2 minus 4. Or 0 is equal to 4 minus 4. Again, this is true. So the point that we chose is a solution for both the first line and the second line, meaning that it is a solution for both of these at the same time. It is the answer or the solution to our system of equations. So your answer would be 2, 0, where x is equal to 2, y is equal to 0. Let's do another couple of practice problems. I will leave problem 1 for you all to do on your own. It's pretty simple. But problem 2 is going to be a little harder. Why is that? We have something that is not in slope-intercept form here. So let's go ahead and change this into slope-intercept form. We're going to subtract 8x, and we're left with 4y is equal to minus 8x plus 16. Let's finish solving. Divide by 4, we get y is equal to minus 2x plus 4. Just dividing the entire right side by 4. Now, what is x equal to 3 going to be for a line? It's going to be a vertical line at 3. What about y is equal to minus 2x plus 4? Well, we're going to go to 4, and then we're just going to make our line. So we go down 2 over 1, down 2 over 1, down 2 over 1, and we keep doing that. Look, we already found our intersection, but let's work our way through this. We make our second line, our second graph, and it looks like our solution is going to be 3, negative 2. Our solution should be 3, negative 2. Now we have to check, does this work for the first equation? X is equal to 3, 3 is equal to 3, that works. We'd have to put this in. 8 times 3 plus 4 times minus 2 is equal to 16. That will work out. I'm not going to go through the calculation here, but that will work out. Go ahead and do this next problem on your own. You will have to convert these into slope-intercept form. Let's get started by converting these into slope-intercept form. This left one is easy. All we have to do is subtract the 3x, and we're left with y is equal to minus 3x plus 5. Let's graph that one. So we're going to go to 5. We're going to go down 1, 2, 3 over 1. Down 1, 2, 3, 1. We're going to keep doing this until we have enough points to accurately describe this line. Then we're going to draw the line. Just so we have a solution area underneath. So our solution for this one will be 3, minus 2. We're going to write our solutions as ordered pairs. Okay, going back to problem 3, the next part is a little bit more complicated. Let's start by subtracting x. We're left with minus y is equal to minus x plus 7. Now that's not good. We have a minus y instead of just a y. We're going to have to divide everything by minus 1, or we're just going to flip the signs on everything, meaning that the other line is y is equal to x minus 7. Great, let's graph that one line now. Up, up, up. And we have our line here. Looking, we have a very clear intersection right here. What is that intersection? Looks like it's the point 3, comma, minus 4. So our answer is going to be 3 comma minus 4. That is what you should have gotten. Now let's look at a variation on the problem. We know how to do this basically. What about for something like this? Let's just graph these. Y is equal to 3x minus 1. So we're going to go to minus 1. We're going to go up 3 over 1 and continue doing that. Let's go the other way as well. And we can graph that line. Okay, what about this other one? Well, let's go ahead and put this into slope-intercept form. We're going to add 9x to both sides. So we get 3y is equal to 9x plus 6. And then when we divide everything by 3, we're left with y is equal to 3x plus 2. Let's go ahead and graph that one. We're going to start at positive 2. We're going to go up 3 over 1. And we can go down as well. So we'll go down 3 over 1, down 3 over 1. That is one too few. Down 3 over 1, and so on. Now when we graph this, we're looking at this. Where will these intersect? Where will these intersect? It's a trick question. The answer is nowhere. We have two parallel lines here. Remember, parallel lines are determined by having the same slope. So if we have two parallel lines, they're not going to intersect. What does that mean for our equation or for our solutions? Well, let's go down to this key concept. The visual solution to a system of linear equations is the intersect. So if there's no intersect, if we have no place where these two cross, then we have no solution. Meaning that our answer for this is going to be no solution. Answer is no solution. And this brings us to a key point here. I think, oh, no, one more. Then we'll get to our key point. What about something like this? Let's go ahead and graph these. Let's start by changing this one over. We're going to subtract x. We get 3y is equal to minus x plus 12. We're going to divide by 3. This gives us y is equal to minus x over 3 plus 4. So we're going to start by drawing this first line. We're going to go up to positive 4. We're going to go down 1 over 3. Down over 3. I'm going to go up 1 and over 3 the reverse way. And up 1 over 3. And we draw this line. Great, let's do the second line now. For the second one, we're going to start at 4. And we're going to go down 1 over 3. Down 1 over 3. We're going to go up 1 over 3 and up 1 over 3. And we're going to draw this line. But wait just a second. We have two lines that are the very same here. They're the exact same line. If we look at this, we have minus 1/3 x plus 4, minus 1/3 x plus 4. What does that mean? Well, how many places do these intersect? They intersect here, but they also intersect there and there. They intersect everywhere. So they intersect an infinite number of times, meaning that this is going to have infinitely many solutions. So we can have more than one answer. We can have infinite answers, or we could also have 0 answers. And this brings us to an important distinction for systems of equations. We have two different types and sort of two different subtypes here of systems of equations. The first type we have are inconsistent equations. And an inconsistent equation is going to have 0 solutions. So an inconsistent equation is going to be parallel lines. The other thing we'll have is a consistent system. And consistent systems just mean there is a solution. Now on top of that, we learned that there were two different ways that we can have solutions. We could have one solution, or we could have infinite solutions, infinity solutions. If we have just one solution, what we do is we call that independent. And if we have infinitely many solutions, that's a dependent system. Well, dependent. So we have three main types of equations. We have inconsistent systems with zero solutions. We have independent systems with one solution. And we have dependent systems with infinitely many solutions. So let's go ahead and take a look. Try to figure out what these systems are. Without graphing, we're trying to determine whether these systems are independent, dependent, or inconsistent. So independent, meaning one solution, dependent, infinite, or inconsistent, zero. How are we going to do that? We're going to set these in y equals form. So this top equation becomes y is equal to 3x plus 4. This bottom one is going to be minus 1/3 y is equal to minus x plus 1. Or when we multiply this through, multiply by a minus 3 to everything, this becomes y is equal to 3x plus minus 3. So it's 3x minus 3. We're looking at this, we have the same slope. So that's not off to a good start. The same slope means that these could be 0, or they could have infinitely many solutions. In this case, we have different y-intercepts, so these are not the same line. They just have the same slope, so they're just going to continue on for all time without intersecting. That makes this an inconsistent system. There are 0 solutions. I'm going to shorthand solutions to SLN. There are 0 solutions, so this is inconsistent. What about for problem 2 here, problem B? Is this independent, dependent, or inconsistent? For problem 2, let's get these into y equals form. We get 3y is equal to minus 2x plus 1, or y is equal to minus 2/3 x plus 1/3. Then for the second equation, this is going to become y is equal to minus 4x minus 3. We're looking at this. Does this have the same slope? No. Is this the same line? No. So this is not dependent. They don't have the same slope, so they're not parallel, meaning that they're not inconsistent. There is one solution, making this an independent system. How about for C? For C, let's get this bottom one into y equals form. We get minus 3x is equal to minus 3y is equal to minus 6x plus 9. We're going to divide everything by negative 3 to get y is equal to negative 6 divided by negative 3 is 2x. 9 divided by minus 3 is minus 3. And now we're seeing we have the same slope. That's not good. And we have the same y-intercept. That's especially not good. That means we're dealing with this same line here, making this have infinite solutions, or that's a dependent system. Now, systems of equations are actually really useful. We see them a lot when we get to real-world problems. So we're going to go through a couple of these. The first one being, we have two candles, one that's narrow and tall, and one that's shorter and thicker. The tall one is going to be 10 inches tall and burn at a rate of 0.75 inches per hour. Meanwhile, the short one's only going to be 6 inches tall, but burn at a rate of 0.25 inches per hour. We're going to ask how long will it take for the candles to reach the same height, and how tall will they be? We're going to set up the equations and use a graphing calculator. So let's try to set up the equations. I'm going to give you the variables here, but that's something we should always be thinking about. We're going to need an independent and a dependent variable. Let's see, what's changing? Well, it looks like our height is going to be changing. It's decreasing. And what is it decreasing in relation to? What is it decreasing by? Per hour, so per time. I'm going to call then x is going to be our time, and y is going to be our candle height. So now go ahead and try to make the equations for these. Our equation for candle 1 will be, our height starts at how tall? 10 inches, and we lose how much? We lose 0.75 an hour. So 0.75 times our number of hours. So x will be time in hours. We're losing that amount, right? We're not gaining it. We are getting shorter every hour. Meanwhile, for candle 2, our height is going to start at 6 inches, and we're going to lose 0.25 inches an hour. So now we want to determine how long it'll take for the candles to be the same height and how tall they will be. So we're going to need to go to our graphing calculators to figure this one out. We'll be back in just a second. All right, here we are with our calculator. Let's get started with graphing these. To start, we're going to want a graph. So we're going to want to put in our y equals. We're going to go to y equals. We're going to put in each of these. Our first one was 10 minus 0.75x. Our second one was we started at 6 inches, but we lost 0.25 inches every hour. Let's go ahead and try graphing this by hitting the graph button. And we see where our solution is roughly. Let's see if we can get a better view though. To get a better view, to adjust where we're looking at on the graph, we can press the window button. And you'll see a couple of values here. You'll see xmin, xmax, and a whole bunch more. The ones we want to focus on are xmin and xmax, and ymin and ymax. Xmin tells us the smallest x value we want to see. And since x is time, we know it's not going to be more than 0 time before they're the same height. Let's keep it at 10. We saw that it was close to 10 for our maximum. What about our minimum? For y? Well, y was our height. The smallest our height can be is 0. And the max our height can be, we had one candle start at 10. So now we're looking just in the first quadrant. We're just looking in the top right of the graph to see what this looks like. Let's go ahead and see what it looks like then. And now we see we have an intersection. It looks like it's not quite, what is this? 1, 2, 3, 4, 5, 6, 7, 8. It looks like it's not quite 8 hours though. So how do we determine this accurately? Well, your calculators have a really handy tool for this. Let's go ahead and look at it. You'll see above one of your buttons a calculate button above your top 5. If you go to that by pressing second and hitting that calculate, you'll see we have a list of possible things we can find. Now we said for graphing, we're trying to find the intersect. So let's look for the intersect. It'll ask you what the curves are. What this is asking is which line is which. So the first line we want to check is the blue line. The second line is just the second line. And then it'll ask you for a guess. Let's get kind of close by moving left and right, and we'll get sort of close to there, see what our answer is. And there we have it. Our answer is right there. Our x is 8 and our y is 4. So let's go ahead and put that down on our equation. When will these be the same height? How long? Well, it's x is equal to 8 or 8 hours. And how tall will they be? Well, y was equal to 4. So this will be 4 inches. And there's our solution. Our solution is 8 comma 4, or 8 hours and 4 inches. All right, I'm going to leave you to do problem 2, and I'm going to move on to problem 3. We have $1.30 in our pockets, and it's comprised of nickels and dimes. There's 19 coins in all, and we're going to try to figure out how many nickels and how many dimes there are. So starting off, this is a second type of problem we might see. Let's figure out what our variables are. Let's call n our number of nickels, so n will be our number of nickels, d will be our number of dimes. Now go ahead and try and write the equations to figure out what this is going to be. This one is a little bit harder, so let's walk through it. We know we have 19 coins in all. These coins are just nickels or they're just dimes, meaning that we can say our total number of nickels and dimes will be 19. So we're saying we have a total of 19 coins comprised of these two. Now what do we do with this $1.30? Well, we know that nickels are worth 0.05 cents. Or you could put 5 cents, and dimes are worth $0.1, or you could say 10 cents. And altogether, how much do we have? We have $1.30. Now you could also write the second equation as 5n plus 10d is equal to 130. That's just making it so that we're in cents instead of dollars. However, you do have to be consistent between the two. You do need one or the other to be the same. So this is a common type of problem we'll see when we're solving systems of linear equations, where we'll have some quantity established, right? We have a total number of gadgets, gizmos, tools, whatever it is, comprised of two different things, and then those two different things can have a specific quantity attached. Could be a number of legs, could be a price, it could be a dollar value, any of that. Now let's go ahead and throw this into our calculator. I realized before we throw this into our calculators, we need to go ahead and solve for one variable. So let's go ahead and do that. We're going to say d is y. So d or y is equal to minus n or minus x plus 19. And then we'll do that for the other one. We get 0.1d is equal to 0.505 n plus 130, or d is equal to, what will that be? Let me look at a calculator. It will be 0.5n plus 13. Okay, let's throw this into our calculators. So here we are. We have both of these equations in. Let's go ahead and adjust our window size now. So we're going to go into window. We don't expect us to have any less than 0 nickels and dimes, so we can leave the minimums at 0. But we could have up to 19 nickels, and we could have up to 19 dimes. So now that we have that all set, let's graph this. And we see we have our intersection out here. Again, we could sort of squint, try to see what it is, or we could calculate it by pressing second, calculate on this top menu here, and looking for our intersect. We're going to choose the first line. I like the blue line, so we'll call that the first. We'll call the red line the second, and we want to get close to where we think they intersect. So we'll move that left or right, and we'll press enter. And we see that our intersection is x is 12 and y is 7. We said x was n, x was our nickels, and y was our dimes. So that means we have 12 nickels and 7 dimes. We have 12 nickels and 7 dimes. Now we have 2 more questions here. I want you to go ahead and try those. Make sure you understand this. and then you can go on to your homework.